Well, welcome to the session of the seminar. This time we have a friend of the house, I guess. He's very well known for many people here in Ellipsoidal in general. His name is Juan Pablo Vielma, and he's a professor at IT. And he's been visiting us several times, and today he offered to give us a talk about the work they're doing in Julia and Jump for optimization and several different optimization problems. They're working there. They have very different things. So he's going to be talking today about using Julia and Jump for personalized product recommendations.
Thank you. So I guess I should do it in English then. Yeah. Great. Perfect. Okay. So yeah. So I'm actually visiting Chile because trying to get people to know Julia and Jump, because I think it's there's plenty of opportunities for people to use it in Chile, but also to contribute to its development. But I didn't want to get just a talk on Julia and Jump, so I figured I'll tell you how we actually use Julia and Jump to do some research and marketing with Dennis. I basically bullied him until he actually said, "Okay, we'll do this thing in Julia," and I think it's now. I guess he's a little bit. He accepts it. I think he started using it with some students. So I think either I brainwashed. I think I brainwashed him enough that he's now convinced. So hopefully I'll brainwash you too. And so let me quickly start by saying, telling you what Julia and Jump is. And I was hoping that I was going to be preaching to the choir here, because we came in 2014 when Julia and Jump were starting, and one of my PhD students, Miles Lubin, gave a tutorial on Julia and Jump here at the university. And it was great because he actually speaks Spanish, and he was here for a week, and he actually learned Chilean. So all the examples were like Chilean sandwiches. So he did a diet problem, but he did a diet problem with Chilean sandwiches. So, but I guess haven't convinced you all, because talking to Marcus yesterday, he said like, no, why are you going to use Julia? C++ is much better and stuff. So I guess I do have to sell it. So let me spend a couple slides. So what is Julia? And it's like the way I kind of describe it, it's like it's 21st century way of doing programming and modeling. And it's literally, it's like that is the difference if you think about Python and most of the languages people use. They are 20th century programming language. That's when they started. Julia started maybe like 5, 6 years ago. So it's pretty modern. And the idea was, you want to use MATLAB and Python because it's easy, but if you're going to do research, you need the speed of C or C++. It's like, I wish we could have everything. And the interesting thing is like compile technology had evolved to the point where like, oh, now actually they just had to design it. So they started with the Alan Edelman's group, and they basically built a whole language that looks, I guess looks like Python and MATLAB, things like C and Fortran. It really looks like Python or MATLAB. So all the string processing from Python, everything you can get from linear algebra from MATLAB, everything built in. And it's fast. It calls C libraries. It's very easy to call C, and uses LLVM, so it's just-in-time compiled. But in addition, it has some interesting features with regards to multiple dispatch, dynamic multiple dispatch with types. Depending on what type the function is called, runtime, it'll figure out what's the best version of the function that needs to be called, and everything all the way down to the final C-implemented code. It'll recompile everything on the fly, and now you'll get a very, very specialized function for that particular type. So if you have, let's say, some algorithm that will work with matrices, and suddenly it sees a sparse matrix, it'll exploit the sparsity. If somebody comes on and defines a new matrix type, it'll also, on runtime, realize, oh, maybe I can exploit things from this matrix. So that's the thing that kind of makes it really fast. And the other feature, it has some features that are called like meta-programming. So it's things that are kind of like scheme, sorry, not scheme, well, actually it's scheme too, but mostly Haskell-like features of functional programming that allow you to, so Julia can read its own code, and which makes it very easy to build a language on top of Jump. You can build a domain-specific language on top of Julia fairly easily. And that's exactly what some students at ORC did. They developed Jump, which is Julia for mathematical programming. And again, they build a way of how do I write down mathematical programming models easily in a way that will look like GAMS or AMPL, but that would be fast. And it ended up being even faster than Gurobi's C++ interface. Because Gurobi had operator overloading, and that was very slow runtime. This works really well, and I'd say it's pretty quickly becoming the gold standard in mathematical programming modeling, because there's a lot of advanced features you can use. So if you know a lot about mixed-integer programming, you can do solver-independent callbacks on Jump, and it's pretty much the only software that allows you to really do that. So you write the same code for simplex, for Groby. You can solve SDPs, nonlinear problems, called a whole bunch of software, different solvers, and now like some of the solvers are even implementing their own interfaces. So Mosaic, for instance, they developed their own interface for jump. And again, the great thing is that it's easily integrated into Julia, so you can call and do other stuff in Julia fairly easily, and there's tons of libraries. So again, for this project, at some point, we needed to solve IPs, we need to solve NLPs, we need to do linear algebra, we need to do Monte Carlo sampling, a whole bunch of stuff. It's like, and we need to be fast, so it would have been a nightmare to do in C. So in some sense, this worked really nicely for us.
Sorry, let me interrupt you a little bit. We're streaming this.
This one
here. So can you switch to the?
I don't know.
To the that one. This one, the broadcast.
Okay.
And then let me just right here. I'm sorry for the interruption. And now I want to share screen too. Share. Okay. Sorry. There you go. Now you can go back.
Okay. Oops. What did I do? Yes. Question.
But then it's too, for the, at least to connect to some solvers, right?
You connect to any solvers, and there's a ton of solver. I should have, maybe I'll show you if you go to the Julia opt page, there's a list of solvers. So Cplex, Gurobi, Mosaic, Skip, CVC, IPOpt, Bonmin, Quen, what am I missing? Mosaic, I think SDPT3, it's like there's 3 SDP solvers. Yeah. So basically every commercial solver, Knitro for nonlinear programming and nonlinear IP. Let me see anything. So the conic solvers, you got SCS and ECOS, which are fairly general conic solvers that go beyond SDP. They also do exponential cone. So basically, you can solve any like linear, second order cone, semi-definite, nonlinear, mixed integer, or continuous. And now we're kind of going in a slightly crazier direction where you'll be able to plug in almost any solver for convex MINLP. Oh, you can also call Baron too. So you can also solve non-convex MINLP problems. And in fact, so regarding speed, we actually developed a solver that is now the fastest convex mixed integer nonlinear programming solver, and it's written in Julia. So it works well because now you don't have to tinker necessarily with details. You can really think about the big picture and the algorithm. And of course, like I said, explicitly mentioned, it is both are open source and free, completely free to use. But there's now a spin-off company from MIT called Julia Computing, which is the company that's there to provide sort of commercial support if somebody actually wants it. But you don't really need it. It's there as a safety net. Some people really just want to pay to yell at somebody. That's them. And then it was developed by students. It started as a hobby from RC students. So that's sort of the reason why Julia was so easy. They just said, oh, let's do a modeling language. And I don't like IAMS, let's do a modeling language. So they started by themselves. And now we actually grew. We have a very big community of developers. So we had a workshop in Sloan in June. And people from a lot of different countries that basically they're contributing, they're volunteer developers. Now, actually, to get more sustainability, I hired a software engineer that actually is in charge of basically keeping Jump running, because Miles, who was the leader of this whole thing, that's when he started, moved to Google Research, so he's still going to be involved, but he cannot code that much. So now we have sort of like somebody that's there whose sole work is to make sure this works. And then there's me, so like I always like trying to figure out like, so what the hell am I for Jump? So I'm an advisor of 2 of the students that started working on this, another student that's actually working a lot on this. I'm Derek Boss because I hired him. I'm the one that's trying to get funding from different places. And this has a very, very good idea. Basically I started hiring people because Miles moved to Google, so I couldn't boss him around anymore, so I needed somebody to replace him. But then this came with a really good name for me. It's like, I'm the jumpsuit. Because I'm the only one that gives talks on Jump with a suit. Everybody else are like the coders and stuff. But I actually changed it. Like my grandfather was always Don Federico, and I wanted to be Don Juan Pablo, so I'm thinking and then define my title as Jump's godfather. Because actually, the funny thing, I gave a talk at USACH, and I went there, and the first thing somebody said hi, I was like Don Juan Pablo. Oh, great! I haven't even given the talk, and it's working already. So I'm happy to tell you more about Julia offline or over lunch and Jump. So, but I figured basically better tell you a little bit of research that we did that actually uses jumping, and Julia for that. And it was basically looking at how to do customized product recommendations using choice-based conjoint analysis. And it really is an experimental, it's an experimental design for linear models, for logistic regression in this case, but it doesn't really have to be logistic regression. It could be generalized linear model. We haven't really written it, but the math kind of falls through directly. And again, but the motivation is product recommendation. So suppose somebody comes to your web page and wants to buy a camera, but it really doesn't know what camera to get to buy. It gives you very broad ideas. There's a lot of trade-offs. Well, I like a smaller camera, but I'm not sure how much I'm willing to pay. What you can do is present different products and make the user compare them and pick one of them. And then they'll actually try to figure out his preferences and then recommend a camera. And the way one of the questions is what it's called a conjoint analysis. And the key is that in conjoint analysis, usually you ask like 20 questions when you do these studies, these marketing studies. You cannot do that with somebody in a web page. 5 questions probably is already too much. So it's going to get bored and it's going to leave. So I really need to pick the questions in an adaptive manner. So when I ask you a question, see what you respond, and then figure out what's the best questions to ask next to learn as much as I can from your preferences. And I want to do that online and quick. And you basically, your aim is to, you have some model, some probabilistic model of your parameters for your preferences, and I want to get to minimize the variance of some estimator of the preferences. That's what I want. So that's why it's an experimental design problem. I want to minimize the variance of some estimator of some parametric model. And did I mention, like, and we want a parametric model because we also want to be able to not just recommend your product, we also want to learn what your preferences are, because maybe you're like, oh, I'm seeing that a lot of people have some preferences, and I don't have that product, I would like to build it later. So I really want to have your trade-off between features. So again, choice-based conjoint analysis kind of works like this. You are presented with 2 products, and products are defined by features. So Chewbacca is a Wookiee, he's not a droid, and he carries a blaster. And BB-8 is not a Wookiee, is a droid, but doesn't carry a blaster. So I'm going to go with Guido. Which one would you pick?
Chewbacca.
Yes, good. So this actually, the good thing is that you made the right decision. The bad thing is that you messed up the presentation because the whole point was telling you were wrong. But if you would have been wrong, there was a reason for that. And it's because people make mistakes. So you could have said, I mean, everybody should have always said Chewbacca. No question about it. But you might have said BB-8 because, well, sometimes you're unsure and you make a mistake. So the model has to take that into account. So the model we're going to pick is sort of fairly standard multinomial logic model. And just to fix ideas, I'm going to forget about the specific products. Now I'm going to go to just math. So I'm going to think about the products are represented by a binary vector that says if a given feature is there or not. Yeah, I could have multi-levels, and there's issues on how do I encode this, but I'm going to stick with just binary features. And the model that actually will take into account the possibility of errors is basically this multinomial logic model, and it's basically a logistic regression problem. So the idea is you think that people have some utility on a given product, and that utility is a weighted combination of the features that are present on that particular product, and which are called the part worth, or the weights that you give these particular features. And there's some error that's the one that could induce you to make mistakes, and usually you can pick it to be gumbo, but could be normal too. You would get a probit model. It really, there's not too much restrictions in principle in what the error is going to look like. And the idea is that people are going to prefer the one that gives you the best utility. Of course, there's no best utility because it's random. So, but you can actually come with the probability of a very simple formula, the probability that you'll pick a given product given your preference vector. And that's what we're going to use as a likelihood to be able to, well, given that I'm going to ask you several questions and you pick the given product several times, I'm going to use that to infer what the beta was. Okay? And as I mentioned, this is really just logistic regression because I could have picked the difference between my product profiles, and that will give me a -101 vector. And what I'm really asking is, what's the sign of, is your beta times z greater or equal than 0 or less than or equal than 0? You're going to say 1 or 0, and depending on if 1 is be positive, 0 is negative. And if you look at the probability, this is exactly the logistic function. So this is exactly an experimental design for logistic regression. I want to ask several questions. I'm going to do logistic regression. I'm going to estimate the beta, and I want to minimize the variance of that beta. That's the name of the game. So in some sense, like, the marketing thing is, that's how we started, because they had some nice geometric ideas, but it really is an experimental design. So any questions about the model? And again, the details of the probability is not too important. The only thing that is important is that, again, I have this sort of linear model inside the probability. So everything depends on beta times zx, essentially. Actually, those two should be x, x1 and x2. There's always a fact. And we picked, so I didn't know much about Bayesian. Did you? How did we get into Bayesian? You tell me.
Yeah.
Have you done Bayesian things before?
Not really.
Okay, but then it's convinced me. So I convinced him about Julia, he convinced me about Bayesian stuff, and I kind of now started liking it. And again, we're going to take the Bayesian approach, and the idea is we're going to have a prior distribution on our betas. They think your beta is in this region, and we're going to think it's a Gaussian. We're going to have a likelihood function that's going to tell me, again, coming from the probability, what's the probability that you choose a product given the beta. We're going to flip it and say, what's the likelihood of beta given that I showed you these products and you pick these other products, if you pick this one. And I'm going to use just Bayesian update, and I'm going to get some posterior distribution of the parameters. And my estimate could be the mean, the mode, whatever you actually like. I think we're using mean, basically. And but the main thing we want is this distribution changes, but I also want to figure out, I like the distribution not just to move to the right parameter. I want the distribution, the variance of the distribution to go to get smaller, to get more certainty on the parameter. And again, so that's the problem. We start with the prior distribution, normal. I'm going to ask questions, and the way I want to select the question is I actually want to select the question that will reduce the variance of this posterior distribution the most. Okay? Because in this particular case, both of them, let's say this was the true value, both of them are converging to the true value in the right way, but this one's getting there faster. And I want to do that selection depending on what you answer. So I'm going to be updating this thing, the beta is going to be, the distribution is going to be moving in a certain direction. So I want my questions to go and like chase that and try to like squeeze it in a way that I can get a very good estimate. Okay? And the problem I have is that this posterior distribution is not nice. I don't have conjugacy, so I cannot give you a simple formula. So the only way I can really access it is through MCMC, through Markov chain Monte Carlo or some sampling method or numerical integration, but it's n-dimensional, so I won't be able to do it. So, and I'll need a lot of samples because again, I want the mean and I also want the estimate the covariance matrix. So I'll need a large number of simulations to be able to get an idea of what that matrix is. The other issue is like if I'm doing one-dimensional models, then it's really all about variance makes sense completely. But when I'm thinking about the multivariate, it's like I got a covariance matrix, so I need to summarize that covariance matrix in one scalar that I can minimize, and there's different ways. Both of them have to do with the determinant of the covariance matrix or the eigenvalues of the covariance matrix. We picked the one that's called the efficient or the error, which is the expected, the determinant of the, I picked the determinant of the covariance matrix. I'm going to scale it with the dimensions so that this thing is convex. It's convex? Concave. Because it's going to be the geometric mean of the some minus there that I had trouble with. But we can scale it so that it will be basically the geometric mean of the eigenvalues, or I could actually put a 2 here, and it will be sort of like the volume proportional to the volume of the confidence region or credibility region around the mean. So I can pick either way. We started with 2, now we're actually using the dimension. And the other thing I'm going to do is I want to pick, so I can calculate this determinant once I ask you a question and you answer it. I can go and sample, get the covariance matrix, calculate the determinant, and evaluate this dispersion measure. But then I have to do it, well, what if you answer the different question? I'm going to get something else. So I want to look at that expected error. So I need to take expectation with regards to your answer. But your answer will depend on beta. And I don't know what beta is, but I have an estimate of beta. So I have to take expectation over beta again. So I have to integrate over beta, over your answer. And then for each one of these things, estimate this covariance matrix, calculate a determinant. So evaluating this thing is going to be very complicated. I could try to evaluate it approximately, but the key is that this is a function of the whole question, and the question could be large. Not too large, but it could be, let's say, 12th dimensional. So now I would have to do 12th dimensional integration just to evaluate the quality of my question. So you can't really, in the integration, I think I calculated, we did it, actually, I think do have the details. So one way of doing this with Julia would be, I can actually access state-of-the-art sampling tools, Markov chain Monte Carlo sampling tools, directly from Julia. So Stan is one of the best well-known such algorithms or such software by Gelman and company. And it works really well. I can sample and it's really, really fast. So we did a code in Julia that sampled. It was good. But this thing was much more stable and much faster. It gave you good quality guarantees of the chain actually converge and things like that. The problem is that to evaluate one of these questions, it takes several minutes to actually evaluate. And if I had to enumerate every possible question, it would take me months to be able to work with this. So, and in some sense, I'm kind of forced to enumerate because the only thing I can do is kind of like look at evaluate the function, and the function is highly non-convex. So it's not clear how I would actually be clever. I could do some, what are these called? Forgot the name of these, Gaussian optimization, when you put a Gaussian model and you try to approximate this black box function, but it's still minutes to evaluate the function will take too long. We started looking at, you can do some approximations using Fisher information matrix, and that gets a little bit better, but you still like end up having to enumerate. It will take you probably minutes to find the best solution. And again, the problem is that it's a relatively high-dimensional non-convex problem that we don't know how to solve. So we want to try to transform it to a problem that is still non-convex, but in some sense we write all the non-convexities in a way that we can deal with. Now, there's another approach that I don't want to do the Bayesian, which is we're basically believing that this Bayesian approach is reality. So that's what we want to try to do. But there's some other approximations that are sort of geometric, and what they do is instead of thinking I have a prior distribution of my beta, I think the beta lives in some polyhedron. And then my questions, because of their linear nature, are really going to be telling you, I'm asking you a hyperplane, and you respond, it's on the left or on the right. And I could really just chop the polyhedron in the direction I get, and I update my sort of like a uncertainty set, if you wish, of where the beta is. You can think this of a uniform distribution in a convex set. And unfortunately, it doesn't really consider errors. So there's been some work in trying to add error, because now you say, like, if you answered greater than or equal to 0, I believe you, and you might have made a mistake. And if you made a mistake, everything kind of goes wrong from then on. So there's been some approaches to try to add error. They don't really work that well. We kind of realized that if you actually used ellipsoids, and in some sense, instead of you started with ellipsoid, chopped it off, and instead of actually picking the chopped off set, you pick the minimum volume ellipsoid that contains that, which is easy to calculate, or some correction of that. That worked better, and it kind of added some error. But again, it doesn't really do the thing that we really want to do, which is get the Bayesian thing and get it fast. And again, the issue is, so we have these two things in something like a Bayesian. You have to do MCMC to be able to evaluate things, or enumeration to optimize. It uses the error that we decided was the correct one. The geometric ones don't use that error, but use simple linear algebra and mixed integer programming to be able to solve the problem. So we wanted to kind of like combine them. And well, the way we got it is using MIP and Julia and Jump to implement it and test it. So let me quickly, let me see how much I'm in time. Till when do I have?
12:30.
12:30. Okay, so I think I'm done. Actually, I think I'm going to end up early. Okay, so let me just go back again to the model. So again, I want to do this with this particular model. And again, the issue is that this function here is non-convex. It's hard to evaluate because I can only evaluate it by sampling. And my variables are relatively high dimensional. They're not really 12. I could go up to 20. It's not really going to be huge, but it's still enough that enumerating is not going to be an option. Both because of the dimension and the hardness of evaluating the function. So the way we actually started looking at, again, the problem that I want to solve is I want to minimize. It's fairly simple. I want to minimize the function of the difference of two binary vectors. This is a function that's fixed, but depends on my prior distribution. And it's a fairly annoying function, but it's high dimensional. That's the main thing that complicates things. So when we actually looked at it, if you actually looked at the linear algebra of the expectation, you can realize that this high dimensional function that depends on all those 12 parameters actually doesn't depend on those 12 parameters directly. It only depends on two quantities associated to those two parameters. It depends on that mu is the mean of my posterior distribution. So this is sort of like the mean of my question. When I do beta times my question, I expect to see D. And this V is the variance of the question. If I did Z times beta, its covariance matrix would be this quantity. And it's only those two quantities that actually come into play into this function that I want to solve, that I want to optimize. So, and it's basically just a little bit of linear algebra. So the other good thing is that's a function of these two parameters. There's still an integral somewhere in there, but it's a one-dimensional integral. So I can calculate it, and we actually first did some MCMC. It worked out okay, but then we realized, oh, I wonder there's a package in Julia that does numerical integration, and there was. We downloaded it, and it was like 100 times faster. And it worked really fast. Fractions of seconds of actually doing that one-dimensional integral, and I don't even know exactly how it's computing it, but it works. Again, I didn't need to know. Now, it's still a non-convex function. It's fairly annoying to deal with it, but it's a two-dimensional function. And if I have a two-dimensional non-convex function and I can evaluate it fairly quickly, what I could do is just do a piecewise linear interpolation of the function. And now we're giving a fairly good approximation of the function. And again, it's qualitatively, I want just the variance, so I just want to capture the general shape of the function. Now, the function is, so this is not going to cause any trouble because this is just linear on my variable on z. This one's going to be a little annoying. So this is positive semi-definite. If the constraint was in the right direction, things will be okay. But it's not. It's exactly in the opposite direction. So I said equal here. I can do a less than or equal, but it's exactly in the direction that makes it non-convex, so we keep it equal. But the great thing is that this is a quadratic function of z, a non-convex quadratic function of z or constraint, but z is binary. So I can do the usual tricks of linearizing this thing, and it'll be okay. Finally, the thing that we realize is that this way of the shape of the function on minimizing this general variance align with some heuristics that have been looked at before, which was I want to do two things when I select a question. The first one is I want to minimize the mean of the question, which if I go to the distribution, let me pick the distribution, the Gaussian. I guess I do need two dimensions. If you look at the likelihood function, this likelihood function is somewhat like a hyperplane, like a soft hyperplane. It's a soft max of a hyperplane. There's two things I want to do. I want to chop with that hyperplane. I don't want to chop on this side. I don't want to chop over here. I want to chop sort of in the middle of the distribution to really split it in two. I'd like to know, you say you're in all this region. I want to know if you're in one half or the other half. That's one rule you want to do. That is, if you think about it, like it really is, I'm trying to do sort of like a geometric search by dividing into two. And the other thing is, with that, I'm going to minimize you making an error. If I made I'm going to balance the way in which you answer, and those are the questions in some sense that I don't know what you're going to answer. Because if I chopped over here, I know most of the mass is over there, so very high chance you're going to answer that. If you happen to answer this way, it would be great, but if I bet you're going to answer that. But if I ask you, well, is your beta on that side or this side, I have no idea what you're going to answer. So it's the one that's going to reduce my uncertainty the most. The other one is, well, there's a lot of ways of going through zero. So the next thing is, this Gaussian now is fairly round, but eventually it'll start being elongated. So if I look at this direction, there's a lot more variance in that direction than in that direction. So I really want to chop like this, because I'd like to reduce the variance in that direction. Not in the directions that I also know, like, I kind of know the beta and what direction it is. And those are exactly the two principles that actually this function picks together. And it balances it the right way. So the balance is basically that curve that's giving you how to balance the this trade-off of minimizing the mean and maximizing the variance. And there's something, I forgot the names of utility balance was the minimizing the mean, which is kind of going through center, and was the other ones? Post-choice symmetry, which basically you don't want the level sets of this Gaussian to get elongated, you want them to get kind of round. That was the principle. And again, from a Bayesian perspective, that's exactly what you want to do. So putting everything together, it's a fairly standard mixed integer parameter product, integer parameter problem in principle. You just need to write down linear constraints to capture what the mean is. This non-convex quadratic constraint to capture the variance, but I can linearize it with the usual tricks. I need to also write down that the products are not the same because you could give me the same product, so I had to force that. But once I linearize this is trivial. I want the things to be binary. I have this nonlinear function, which was a piecewise linear function because I can interpolate it. And I could have some other constraints. So I can have constraints, for instance, constraint at some point I had if I had, like, go back to the example, droids are not Wookiees, so you cannot have a product that's a droid and a Wookiee. I can add that constraint. And those are important because depending if the products are realistic or not, your errors will change. So that's something that actually is useful to put in. And again, with MIP, these things are in. The only thing that was complicated here was, well, I need to build a model, a formulation for my piecewise linear function. I could use standard formulations, but those are not necessarily very good. They won't scale very well. There's more advanced formulations, but then I had to learn how to do the formulations. So one of the things we use is one of my students was working on building nice formulations for piecewise linear functions, mixed integer primary formulations. And at some point we decided, you know what, it's like nobody uses, so I have a paper, a lot of citations, but I probably think that maybe a handful of papers actually use the formulation. They usually say, and there's many advanced formulations, so but we're not going to use them. Why? Because they don't want to spend time reading the details and actually coding it. It's not too terrible. You still like one page more of code. So we put all these formulations in a library that you can easily access from Jump. And basically, if you're using Jump looks kind of like this. You have load some packages, you define a model, you define some variables, and then you have an objective. Constraints are fairly easy. They're defined linearly. But now I can actually directly work with a piecewise linear function, and I can define it basically. I'm defining a piecewise linear function. This is going to be the value of that piecewise linear function, z. It's a function of two variables. I'm discretizing from 0, 1 to in both variables with an interval of 0.1. And the function that I'm interpolating is exponential of u plus v. That's all I need to do. This will build the model internally, pick the MIP formulation, a default MIP formulation. And if you want to use an advanced one or you want to switch, one parameter and it'll build a different formulation. So it's also easy to test different ones. So now so that's what we add. Yep.
And was this better than using just like some distinction?
Basically, yes, because the problem is that it's non-convex. So the only options that you would have is Baron or Quen. And they're way too elaborate for this. So Baron or Quen will work really well. They're so general that they'll take forever. Just because, in particular, one of the things that they'll be able to do is actually get the exact optimal. Here I'm approximating this. So I'm not really going to get the exact optimal, but it's still a discrete problem. So in fact, if I went and if I look at the range of D's and V's, it's not really continuous. It's this evaluated in the grid, so it's really not every possibility. So I could actually go but we do a much coarser grid anyway. So that's the other reason. And it sounds like you cannot tell Baron, just do you're not going to go to optimality, so you can take it easy. You cannot tell it that. You can just stop it, and it's like, but I want it optimal, and that's essentially the issue. We actually, one of the things we're working on is kind of like a same procedure. If you have a non-convex problem, and you kind of have this structure, you can always divide it into things that are going to look like two-dimensional. So you could go and we could use this library, and actually we're working on that. You give me this non-convex problem, and you say like, but the non-convexity, just discretize it. I can build the discretization automatically and solve it and give you back the solution, make sure it's feasible, and then I'm going to give you a bound. And that bound I can make it to be a guarantee of the optimality, a true bound, or approximate bound. It's just that refining will be hard, but usually people kind of like will be okay with, here's a solution and here's it's guaranteed to 5% gap. And then you decide if that's good enough. You won't be able to really go further and reduce that like Baron would do, but it will be way faster to get that decent solution fast. And again, it's just doing this. So we're actually building now the package so it's easy to use, and you just give me the functions, the nonlinear functions. You would give me something like this and give me these functions, and everything would be okay. You still have to give me a formula for this, but actually not really. You can give me a code that does this, like the MCMC code, and it would still work out. Because Jump is integrated into Julia, so your functions can be actual Julia functions, not necessarily just expressions. Which in a sense, if I write down an expression, computationally that expression, there's still an algorithm that's going to compute that thing. So if I give you a whole Julia code, that's the same thing. So I can also calculate gradients from the function. There's a whole bunch of things I can do by reading the code. See, okay. So how did it work? So we put everything together, and basically what we call the ellipsoidal method. So what we kind of like realized what actually the method is. It was sort of heuristic, but now we can actually say exactly what it does. It's an optimal one-step look ahead, moment matching, approximate Bayesian approach. Let's see. I think one point I tried to do the acronym is like Ulambaba or something like that. It didn't ring as well as ellipsoid method. And what are the steps? Well, one is this optimal one-step look-ahead function policy, which is I'm going to start assuming that I have a Gaussian prior. If I have a Gaussian prior, I know exactly how to compute the function, the next question that minimizes the variance of the posterior via the MIP. We can solve it. We need to compute again the piecewise linear, evaluate the function in a grid. We do that with this package, Julia package, and basically everything takes less than a second. So we're solving the MIP, and it's like always like wanted to do real-time MIP, and in some sense, in this particular case, real-time MIP means just call Groby. It solves really fast. So we can do it real time. And again, the marketing people say like you really need to keep it under 1 second because people will not stay on the survey more than 1 second. Like really, 1 second? It's like yep, less than 1 second. And actually, they were saying hey, if you could keep it down, as you keep it below 1 second, it'd be good. But it kind of worked. It does. Groby does it in 1 second. In basically an iMac. It wasn't even a big computer. It's not a server. So that worked. Now, we only can do it if the prior distribution was Gaussian. So there's two things within approximation. First is that we're only looking at the next question. I'm thinking the next question is the last, how do I minimize the variance? I'm not doing dynamic program. I'm not thinking about 3 questions down the road. The other thing is, again, once I did this update, the new distribution is not Gaussian, so I cannot repeat it. So the thing that we're going to do is, let's just pretend it's Gaussian. So that's the way we were looking at it, like, oh, you know what? That's fine. I can estimate the covariance matrix of this posterior distribution by sampling. I can estimate its mean, and I just say, let's say that this is Gaussian. Interesting enough, we discovered this actually has a name. It's moment matching approximate base, which sounds much better than, let's just believe it's Gaussian. But that's basically it. It still requires to calculate the posterior to be able to estimate this mu and this sigma. But the same linear algebra that allowed us to do the question allows us to do this with one-dimensional integration. And again, we used quad GK and it, again, less than a second. So the whole update, question selection and update runs in less than a second. So it worked out okay. And again, once I do this update, I kind of like go back to square one and I assume that again, I'm in the Gaussian world and forget what happened afterwards. So we tested this thing and we looked at 16 questions because we wanted to, again, our aim is less than 5, but we wanted to look at, well, what would happen if we ask more questions? We want to look at how the estimators behave when the questions grow. We're giving 2 options and 12 binary features for each one of the 2 products that I'm showing. And we're simulating the response, the true response with this MNL model that we're assuming is truth. We're sampling 100 individuals, so we have 100 individual betas, and we're going to estimate all those betas from a particular prior that we know is there. And we're comparing with all these methods that I kind of briefly mentioned, these geometric methods. And everybody kind of gets the same initial prior distribution to work with and ask the questions for. And basically, yeah, all of them work in less than 30 seconds. So I would say polyhedral and us are below 1 second. The only one that really jumps up is this a robust version that solves this really nasty nonlinear IP that is just like an overkill and actually doesn't work that well. With regards to metric, we do 2 things. Basically, expected distance to the estimator from the estimator to the true beta, or the root mean squared error. I don't know exactly why they want to switch the expectation with the root, but that's what they seem to do. So we picked that, but it's basically expected distance. Error in the market share. So what you do is now I pick a whole bunch of pairs of products and I try to predict which ones are going to actually several pairs of products. I want to predict which one is the one that this particular guy with this beta is going to pick. And I answer that question with the true beta, and then I answer that question with an estimated beta, and I see how many errors I do. So this is kind of like they call out of sample testing. I really want to do is like, I want to predict market shares, so that's my end goal, not really knowing the beta. So we added that. And finally, this varies of my estimator, the efficiency, which is the thing we're optimizing for. All the other things we're not even considering, will I get a good estimator or not? And we're like, no, we just want a procedure that's going to minimize the variance. Why? Because that seemed like a well-posed problem, that's all. All the values 100% are normalized, and it's going to be smaller numbers going to be better. And basically, I'm going to give you, the method gives you an estimator, but then afterwards, I can actually run down the right MCMC estimator that will take a little bit longer, but at the end, I can compute that afterwards. So I'll need to use the estimator the method gives me to recommend the product, but then at the end of the day, I can go and get a better estimator to figure out what's a product I should send them an email about to selling something else. And because we're really running the true Bayesian model, we figured like we eventually want to run it with people. We hadn't had time, so we did sort of like sensitivity analysis. We did two things. One is all the methods think we're sampling from the normal, we're given mu and sigma. We now tell the models the wrong mu and sample from the real mu and see how the methods fare. And the other one is all the errors were done with the model, the response model is multinomial logic. We assume that somebody else is doing errors differently. We just randomly put all the errors at the beginning or all the errors at the end. And also to see what if people didn't respond in the way of the actual model. So this is the actual measure that we want to minimize, the d-efficiency. So these are the 16 questions. As I ask questions, the variance is starting to go down. One is the variance that I get at the beginning. That's my sort of prior variance. And 0 would be no variance. And at the end, everybody ends up with 16 questions, ends up with a fairly good small variance. But our variance really reduces much faster than everybody else because we're actually doing almost the best thing you could do. The only thing we're missing here is not doing the moment matching, actually using the complicated posteriors, and doing the dynamic program. There's some work that has looked and that says actually the optimal one-step look-ahead policy might actually be the optimal policy for the whole DP. But it's not exactly with this particular model, and it's a one-dimensional model. So it might be that we're actually doing the best. And again, it's much faster reduction on the variance. Basically, if you wanted to get the same variance as the other guys, we cut the number of questions in half. And if we wanted to do 5, it's still the variance is going to be pretty good. So kind of like it would work for recommendations if we wanted to. And these are, again, the sensitivity analysis things that we did. It basically works out the same for us. Qualitatively, it's essentially the same. So that's what we really, then that was, again, our goal was actually the optimization problem, but at the end, what you really want to figure out is like, did we get a good estimate of our beta? And so this is this expected distance of the beta. If we look at the estimators that the method gives us, the funny thing we discovered is like, a lot of people just go and did the 16 questions on the papers and they realize, oh, I actually learned a lot. The first few questions, they go crazy. So you start, the mean, that's the estimate you get from the mean. The method starts with a question, and the estimate gets worse at the beginning. And it takes a while to eventually get good. So they thought, like, what if I ask 20 questions? How good would it be? Well, it'll be good. But at the beginning, it's kind of garbage. And we kind of go straight up and improve the estimates. That actually makes it that if we actually have errors, well, when people start asking errors, it's like the model does anything. But we catch up immediately when you're making the error that we're predicting. And also, if we have the wrong mu, for instance, well, the estimate of the mean is bad, but we quickly get a better estimate. And then that's when I would say, like, these other methods kind of worked out okay. And I would say this is the regime that most papers were looking at before. And basically what they were showing you was this slice over here. So we'd still do better, but in some sense, we start doing better quicker than everybody else. Now, if we actually go and do, well, now I'm going to do MCMC for real and get a better estimator. That's the estimator I'm going to run in the afternoon when I'm going to send him an email recommending something. We, again, also do much better. And finally, market share. So again, this is the error in predicted market share. If we actually use the R method, it doesn't really align well with market share. There was no reason it would. We were actually just minimizing the variance. This is sort of an out of sample thing that we weren't even considering. So if we're doing method, if it's a thing that we're doing online, and at that point we would like to predict market share, that wouldn't be very good. But if we're doing the market share prediction in the afternoon, where we could run the MCMC to actually get the true posterior, then we actually get much better in predicting market share. So it's still a useful tool. We want it for recommendation, but it will be a useful tool for marketing as well, if you have the time to run the more complicated MCMC. Perfect. So again, it's like, what were the ideas? Basically, MIP is a great way of solving non-convex problems because you can do the piecewise linear approximations, and then you can just write a very good MIP formulation, and the thing Groby will solve that really quickly. What's the constraint? It really works for 1 or 2-dimensional functions. You cannot do it for more complicated functions. So the key is, how do I pick this very, very complicated multivariate function and transform it into bivariate functions or functions I can deal with? So usually what you would do is you would write down an expression tree of your functions. So this is f of something, and in the end, if you write down almost any function that you can come up with, you'll be able to write it down with sums, products of 2 variables, and univariate functions. So you can do that. What we did was something slightly different, which was basically realized it was this shape. But if you think about it, this is sums of univariate functions, mu I times beta I. This is also zi times cj with some constant, so it's product of functions. And then the slight thing that we didn't do is, this is a 2-dimensional function, not a 1-dimensional function. Now, the key was, I probably could have done a 1-dimensional function, but the thing is, I don't know what the function is. It's through an integral. And it's really funny because for a long time, I was asking people these things that only use products are called factorable functions. And I was always asked, is there any function that is not factorable? So is there truly a 2-dimensional function that is not factorable besides x times y? And somebody's like, and usually we get, oh, beta and things like that. It's like all the functions that I would find that are 2-dimensional basically were cooked up in a way where you actually had to calculate an expectation or some integral. And this function is exactly that form. But luckily it's a 2-variable function. Again, 2-variable function will be okay. I don't know, I guess you could probably come up with a function that is a 3-variable function that has integrals and you can't really separate easily. But again, if you can, then MIP will really be your friend because you'll get a good approximation. And again, now it's easy to access because once you actually write down that piecewise linear function, actually, once you write down a 2-dimensional function and you can evaluate it, that's all you need, so the jump will basically build the model and you not have to worry about it. So in this particular case, even evaluating the function was a code. It was, you had to sample. That's okay. I didn't really need to give the code an expression on the function. And again, the method that we got is you get a very big reduction on the uncertainty, but also you get a fairly good estimate. And again, and we're actually planning on getting a Julia package that will be easy to use. So hopefully somebody actually goes and does the experiment because we've been pushing to do the experiment with real people, but the algorithms are more interesting than actually getting people. So hopefully somebody else will do it. And finally, the MIP flexibility allows you to, here we're reducing the variance, but really wanted to give you a good recommendation. You could potentially write down the MIP that actually says, I want to learn to give you the good recommendation. And again, the flexibility of adding constraints makes it easy. So that's sort of on our list of things once Dennis fixes a function that he had wrong. It's fixed? When? Last night?
Yeah.
Okay. So I guess I could have given you the new results if I didn't sleep. So thanks again for your attention. So that's it.